Hello and welcome back. In this section we'll try to put together everything we've learned so far in this chapter in order to predict the products of a reaction dealing with SN1, SN2, E1, and E2. So it should be clear by now that a number of factors affect the products that are formed when an alkyl halide reacts with a nucleophile or a base, and depending on whether the base is acting as, whether the reagent is acting as a nucleophile or a base. Okay, and so we've learned that we can get a mixture of products depending on whether we get substitution or elimination products, and even within those subsets of products we can get different products. Okay, so for a simple substrate like this, we can even have three possible products. We can get the substitution product. Notice this is a chiral starting material, so we've got a hydrogen going back and a bromine coming out. So remember, we get inversion of configuration when the nucleophile attacks. So if our hydroxide is acting as a nucleophile, it's going to perform an SN2 reaction where it attacks at the alpha carbon, kicks out the leaving group, okay, and we form this product over here. So notice that we get inversion of configuration. So that means that our hydroxide is on a dash, whereas our bromine was on a wedge. That's because this substrate at the alpha carbon is going to flip like an umbrella, and we get inversion of configuration at that carbon due to the SN2 reaction. So if it was on a wedge, now it's on, if our leaving group was on a wedge, now the nucleophile is on a dash, okay? But we can also, if our reagent is acting not as a nucleophile, but rather as a base, and in this case it can act as a base. We know that sodium hydroxide is in fact a base. So if it's acting as a base, it can pull off a beta hydrogen, and we can get an elimination reaction via an E2 mechanism. So we have a beta hydrogen here, and we have three beta hydrogens here. So if hydroxide is acting as a base and pulls off this beta hydrogen, we form a double bond and kick out the leaving group, giving us the first elimination product as a possibility. If our base pulls off one of these end hydrogens, forms a double bond, kicks out the leaving group, then we form this as a possibility. So the left one is the Ch7 product, and the right one is the Hoffman product. So the Ch7 product will be major if we have a small base, and the Hoffman product will be minor if we have a small base. So in this case, we have both regiochemistry for the elimination products and stereochemistry to consider for our substitution product. But remember, we can even have stereochemistry from our elimination products if we get cis or trans isomers. Sometimes, though, we only get one possible product from this type of reaction. So for example, this reaction here, we have a strong base, and the only thing we observe is an E2 mechanism giving us our E2 product, and that's because this alpha carbon is sterically hindered by this tertiary substrate, and the methoxide cannot act as a nucleophile on this substrate because it's too sterically hindered. And we're going to see as we move along that SN1 and E1 reactions are very slow. And so this reaction is probably occurring in a polar aprotic solvent, and therefore we're not going to get SN1 and E1 as competing mechanisms. So in order to understand how these reactions work and to predict the products, we're going to have to take into account all of the factors for our reaction. So in order to do that, we need to determine the function of the reagent, okay? We need to analyze the substrate to see what features it has in order to determine the expected mechanism that it can undergo. And then consider any relevant regiochemical and stereochemical outcomes that are possible. Okay, so let's first look at the reagent here. So we have here examples of different kinds of reagents. Okay, we have this sodium hydride, DBN, DBU. These are big, bulky bases, this DBN and DBU. We don't have any pictures of those right here, but you can look in your book if you're interested in that. They're just big, bulky bases. And then sodium hydride acts as a base only because hydride is hydrogen with a lone pair and a negative charge. And it doesn't act as a nucleophile because it's very small, and so it doesn't really doesn't have the ability to act as a nucleophile. It just acts as a base. So also we have hydroxide, methoxide, and ethoxide. So these oxygen species generally act as nucleophiles. Okay, so they can also act as nucleophiles, so they can act as strong bases and strong nucleophiles. So they're not limited to just being strong bases. Okay, then we have the halides, the bromide, iodide, and chloride that can act as weak bases, but they're strong nucleophiles. Why are these weak bases? They're weak bases because they are the conjugate bases of strong acids. Okay. Also, the sulfides here are also poor bases but strong nucleophiles. So remember we talked about these sulfur-containing compounds being strong nucleophiles because they're very polarizable. So they're not good bases, though, and so they're not going to pull a hydrogen off in order to do an elimination reaction. And then we have weak bases and weak nucleophiles. That's going to be our neutral species, like the water and the alcohols. Okay. So knowing the function of the reagent can help us predict whether we're going to get an SN1, SN2, E1, or E2 reaction. So if we have a strong base and a weak nucleophile, we're going to get only E2. If we have a strong base and a strong nucleophile, we can get SN2 or E2 reactions. If we have a weak base and a strong nucleophile, we're going to get SN1 and SN2 reactions possible. Okay. And if we have a weak base and a weak nucleophile, we get SN1 and E1. Okay. So those are all the possibilities that we could have. And so if we consider that, then it'll help us to determine what kind of outcome we'll have. Then we need to analyze our substrate. So once you determine what mechanism will be favored by the reagent, you can analyze the substrate to see which mechanism will dominate. So if you have a primary substrate and you have a strong base and a weak nucleophile, so strong base, but it's not a good nucleophile, so you're not going to get substitution. The base is going to give you elimination, then you're going to get E2. And that's true for primary, secondary, and tertiary substrates, because remember, for elimination, we don't have that limitation of having to access the alpha carbon, and so we don't have the steric hindrance as a factor. So for strong base, weak nucleophile, we can get E2 is going to be much faster than the unimolecular reactions that would be possible. So we're going to get E2 for all of those. If we have a strong base and a strong nucleophile, then for primary, you can get E2 or SN2, because remember, E2 is a possibility, but for primary, SN2 is going to be faster, and so that's going to predominate. If you have secondary, SN2, that steric hindrance is going to prevent that a little bit, so E2 is going to predominate and be faster. And if you have tertiary, you're not going to get SN2 at all, so E2 is going to predominate. So notice that the unimolecular reactions only happen really if nothing else can occur. So for E1 and SN1, we're not going to see those at all unless we just can't see anything else, okay? If you have a weak base and a strong nucleophile, you're going to get SN2. Remember, nucleophile is what's going to go in and attack that alpha carbon, kicking out the leaving group. So weak base isn't going to be able to do your E2 there. SN2 is going to predominate because that's a possibility. Remember, the unimolecular reactions only occur, they're so slow, they only occur if nothing else can happen. Okay, so then if we have tertiary, but we have a weak base and a strong nucleophile, we're still only going to get SN1 as a possibility, and that's because SN2 is going to be hindered, and the weak base won't be strong enough to do anything. If we have tertiary and we have a weak base, weak nucleophile, we get SN1 and E1. That's where we're going to see that pile of crap. Because we just don't, it's going to be, both of those reactions are very slow. And we're just going to get a mixture of products. So generally, the SN2 or E2 is going to predominate because these unimolecular reactions are really slow. Okay, unless you just have a tertiary substrate and you don't have a base, you just got a nucleophile, then you're going to get SN1. Or you have just a weak base and weak nucleophile, then you're going to get SN1 and E1 for the tertiary. Now for primary and secondary, these don't lend themselves to the to the unimolecular reactions because the carbocation can't form. Unless you have a substrate where the carbocation can form through rearrangements as the leaving group is leaving. So this is just not going to happen. Okay, so the ones you mainly need to worry about for practical purposes is going to be the E2 and SN2. But in this chapter, we are going to consider the unimolecular reactions. Okay, so it's good to have this chart available, and we'll keep this chart handy while we examine some of our reactions. Okay. So after analyzing the reagent and the substrate and using our little chart, you might want to print a copy for your exam if your teacher allows you to do that. Then you can say which mechanism will occur. So draw all possible regio and stereoisomers and then choose the major using the guidelines you've learned. Okay, so for SN2, you'll observe a single product, which is inversion of configuration at the alpha carbon, if we have stereochemistry to be concerned about. If we're not forming a chiral center, then we don't really need to worry about that, right? So the nucleophile attacks at the alpha position where the leaving group is connected. The nucleophile replaces the leaving group with inversion of configuration. So let's consider something like that. So let's say we had this molecule. Okay, and so this is chiral because we've got connected to this carbon, we've got hydrogen, chlorine, methyl, and ethyl. And if we react that with something like sodium hydroxide, for the SN2 reaction, let's change that because we could get an E2. Let's just go ahead and make that, let's say NaBr, okay? So bromine is going to be our nucleophile. What's going to happen? Let's erase the sodium for clarity. The bromine will attack at that alpha carbon, kick out the leaving group, okay, and we get inversion of configuration. So to draw this product, you can keep everything in the same plane, but just invert your wedges and dashes. Now your bromine is going to be on a dash where the chlorine was on a wedge, and your hydrogen is going to be on a wedge where it was on a dash. So you're just inverting the configuration at that carbon. Alright, so for E2, we're going to draw all the possible alkene isomers, and those result only from beta hydrogens that are anti-periplanar to the leaving group. If you have a bulky base, Hoffman is major. If a non-bulky base is used, the most stable alkene is major. So let's consider that. So let's say we had something like this. Let's say we had methyl, bromine. Okay, that's a bromine. All right, and so we're gonna we're going to let's do this. Let's put a methyl group coming out over here as well, and a hydrogen going back. Okay, so let's say we had a base, let's use, well, let's say we had t-butoxide. If we use t-butoxide, then what are we going to do? Well, first of all, we're going to get the Hoffman product. So that's going to be resulting from the elimination of one of these 3 hydrogens here. So we pull off a hydrogen, form a double bond, kick out the leaving group. So this is going to be our major product with a big bulky base. But if we use something like sodium ethoxide, then what are we going to form? Well, we can't pull off this hydrogen because it's not anti-periplanar. So that methyl group is going to stay where it's at. The methyl group up here, well, that's going to lose its stereochemistry. And we're going to form a double bond on this side from the elimination of the hydrogen that's coming out, right? Okay. So that's going to be our major product for a smaller base. Now you may get both of these products using either base, but the major versus minor is going to depend on which base you use. Okay. So for SN1, we need to draw a carbocation intermediate, consider if it'll rearrange. If not, then attach the nucleophile where the carbocation was, and if it does, then draw the resulting carbocation and attach the nucleophile. If a chiral carbon is formed by the attack of the nucleophile, then we get 2 products, R and S, with a slight preference for inversion over retention, but we're not going to really worry about that here. So, let's say this is a phenyl group here, okay? And we've got a chlorine, and this is chiral. So let's put our chlorine on a wedge and our methyl on a dash, okay? So let's say this is tertiary, so in fact it's benzylic. So we're only going to get, so we're only going to get substitution by SN1. So let's say we don't have a good base. We only can get SN1 reaction because this is tertiary. So that chlorine can pick up and leave, and then we're going to form a carbocation here that's planar. And from the result of that, our nucleophile, let's say it was water, so we're actually adding OH. We're going to get a chiral product that's going to give us the one with retention of configuration plus the enantiomer. So we can just write plus En, okay, for the enantiomer. So for E1, we also form a carbocation, but for the loss of the leaving group, if it'll rearrange, then we draw a rearranged carbocation, then draw all the possible alkene isomers resulting from elimination of the beta hydrogen. So we actually could have gotten an E1 reaction for this. Let's just draw this carbocation here. So we've got pH, and we've got this, so we got a carbocation. So if we didn't get substitution, we could actually get elimination at one of these hydrogens. And so if we get elimination from the top one, then our product is going to be this. Let's just draw it here. pH this will be our product. If we eliminate from one of these hydrogens, then we can get pH this plus this. So both of those are possibilities. So we can get the E and Z isomer. And so this one is probably going to be major because that phenyl group takes up so much room. Remember, that's a benzene ring. So the methyl group is probably going to be want to be on the opposite side from that. So let's see if we can predict the product of the following reaction and label all major and minor products. Okay, so sodium hydroxide, let's see what that is. That is going to be, in fact, we could go back up to our chart. Let's go back up to the chart so we can see how to do that. Hydroxide is a strong nucleophile and a strong base. So we're not going to get our unimolecular reactions here with that one because they're too slow, but we can get SN2 and E2. Okay, so we have SN2 and E2 to worry about. Okay, so what if we got, so sodium hydroxide is a strong base and strong nucleophile. Okay, so if it's a secondary, so it is a secondary alkyl halide. So SN2 and E2 will occur, but E2 will predominate. So how do we know that? Because our chart. So we have a strong nucleophile, strong base. We have a secondary alkyl halide. So SN2 and E2 will occur, but E2 will predominate. And we see here that that is because secondary substrates are hindered and backside attack is a little bit more difficult. Okay, so for our SN2 product, we get inversion of configuration. And you can, so remember, the bromine is going to be leaving and we're going to be replacing that with hydroxide. So all you need to do to draw the inversion of configuration product is just change this wedge to a dash. So remember from chapter 5, in order to draw the inverted stereochemistry, you just need to swap 2 of your substituents on that chiral carbon. So in this case, we swapped the hydrogen and the methyl, and that gave us the inversion product. So that's our SN2 product here. Okay. For our E2 product, we need to consider all of the beta hydrogens. Okay. So if we eliminate from HC, we're going to get only this one product possible because it doesn't have any stereochemistry there at that position, right? So this is not stereoisomeric on that end double bond. But elimination of HB can give us the trans product. I'm sorry, HA gives us the trans product. And elimination of HB gives us the cis product. So since we have 2 hydrogens next door on that beta carbon, we can get both cis and trans as possibilities. So all 3 of those can result from elimination, okay, from E2. So this starting material can give us substitution and elimination at this beta carbon and elimination at this beta carbon, resulting in 2 possibilities. But remember, with a secondary substrate, strong base, strong nucleophile, E2 will be major. So our elimination, one of these elimination products is going to be major, right? This is our Hoffman product over here on the right. So it's going to be a minor product unless we use a big bulky base. So we have to choose between these 2. Now remember, I figured out that E2 is going to be major from that chart, right? Okay, so we have to figure out between these 2 which is going to be major. Well, the cis is less stable than the trans. So trans is going to be our major product. So let's identify the major and minor products that are expected for each of the following reactions. Okay, so we've got sodium chloride and DMSO. That is a polar aprotic solvent. What do we know about those? They're not going to give us the unimolecular reaction. We're going to be looking at E2 and SN2. Okay. Sodium chloride is not a base. It's a nucleophile only. Okay. So strong nucleophile, weak base, but it's a nucleophile only. So the only thing we're going to get here is a substitution product where we get a chlorine replacing the bromine. So what happens? The chloride is going to attack at the alpha carbon, kick out the leaving group. We get inversion of configuration at that chiral carbon. Okay, so that is going to be our only product on this one. All right, for the next one, we've got hydroxide, which is a strong nucleophile and strong base. Okay, so we're not going to get any unimolecular reaction products here because we've got strong nucleophile, strong base. So let's examine our substrate and see what we have. We have a tertiary substrate. So for tertiary substrates from that chart, strong nucleophile and strong base, we're going to get E2 only. Okay, that's going to be our only possibility. So for E2, we can eliminate at either one of these end beta hydrogens, so here, and that would give us the same product, which is going to be, I'll go ahead and draw it, this. Okay, that would be one of those. I mean, if we put the double bond up on the top, it wouldn't matter, it would be the same thing. Or we can eliminate at this beta position, and what's that going to give us? This. Okay, we don't have cis or trans because we have two of the same thing on the same carbon on the double bond, so we don't have to worry about cis or trans. Okay, so those are our two possible products. The next one, we've got a tertiary starting material. Let's clean this up a little bit here. Tertiary starting material, okay, and we've got T-butoxide that is a strong base. It's not a good nucleophile because it's too bulky. So that's going to give us E2 only. So we only get elimination. Now we do have beta hydrogens here. This is not a benzene ring, so we do also have a beta hydrogen here. Oh, I forgot to identify our major and minor products in the last one, right? So for this one, we can get this if we eliminate this hydrogen plus this if we eliminate from one of these hydrogens, which is the same as this one. Okay, so those are our two products. The Hoffman is going to be the major product. I'm sorry, this is the Zaitsev I meant. Zaitsev is going to be the major product. The Hoffman's on the right. That's going to be our minor product. Okay, so here on the top, same thing. We've got Zaitsev on the right, and that's going to be major. Now I've messed up again. And Hoffman on the left. You know what I did, and that's going to be minor. I did on this bottom one, I screwed up because I wasn't paying attention to my base. So let's erase that and go back, okay? We've got T-butoxide, which is a big bulky base. So what does that do? That gives us the Hoffman as the major product, okay, and the Zaitsev as the minor product. That big bulky base can't reach this tiny hydrogen, this hydrogen that's not very accessible, okay? All right, so for D, remember DBN is a big bulky base. You can look that up in your book. It's a big base, and it is a base only. It does not act as a nucleophile. And so we don't have any hydrogens here at the ring. We only have the end hydrogen, so we only have one possible product. We're not going to get substitution because we've got base only. Okay, so this would be a strong base, weak nucleophile, but actually this thing is not a nucleophile at all. All right, and so this is going to be our only product. And then T-butoxide here. Generally, T-butoxide doesn't act as a nucleophile, but for some primary substrates, it can rarely act as a nucleophile. So we've got a strong base, strong nucleophile, which I don't know if you've got this listed in your book. If you have one of the older editions, it's listed as strong base, strong nucleophile. Okay, we've got a primary substrate. SN2 is generally considered to be the major product on primary, strong base, strong nucleophile, but this nucleophile is so huge that, you know, this is a possible product. Some books may tell you that you can't get that as a product just because T-butoxide, remember T-butoxide looks like this, is too bulky to be a nucleophile, so this one's kind of iffy. I probably wouldn't give my students this problem. Okay, so I mean, if you consider T-butoxide to be a nucleophile, then your major product would be this one on the right because it's primary and SN2 predominates with a primary substrate, strong base, strong nucleophile. But this nucleophile is so sterically hindered that it's going to be more likely to act as a base. So your major product really is going to be the one on the left. And again, this is not one of the questions that I would really give one of my students, at least intentionally. And if I did give it, I would probably, you know, take that into consideration when grading the exam. Anyway, so we'll continue with our discussion of substitution and elimination reactions as we move on to the last part of this chapter. Thanks for watching. I'll see you in the next video.